This week we're going to be doing a lab on constant pressure calorimetry. Calorimetry is the way that we measure heat. And so we're going to do 3 different experiments in this lab. The first experiment will involve a reaction between an acid and a base. This is what we call a neutralization reaction. Recall that a neutralization reaction, the products of a neutralization reaction are water and salt. This is an exothermic reaction, so we expect heat to be evolved. In order to find the heat of the reaction, we want to know what the heat is per mole. So we're going to need to know both the concentrations and amounts of our reactants, as well as the amount of heat that is evolved. In our second reaction, which isn't really chemical in nature, it's more of a physical process, we're going to dissolve a salt. You may have either ammonium nitrate or magnesium sulfate. You won't do both. In the case of each salt, when it dissolves, the individual ions are going to become surrounded by water, and we call this solvation. During that process, it could be either endothermic or exothermic, depending on how attracted the water molecules are to the individual ions and how attracted the ions are to one another. In this case as well, we're going to determine the change in heat and divide by the number of moles that are involved in the reaction. The last step is a little bit different. It doesn't involve a chemical reaction. It just simply involves changing temperature. But in this particular case, the math can become quite complicated because we're going to be looking at what the changes are in the water and what the changes are in the metal, and then combining those two to solve for the specific heat capacity. When we use a lowercase c, we mean the specific heat capacity, which is per gram rather than per mole. So what we're going to do is find the heat of the process, just like we did in each of these, and then we're going to divide by the mass and the change in temperature of the metal, and that will give us the specific heat capacity of the metal. Talking about thermodynamics, that the entire universe is composed of either the system or the surroundings. And so anything that's not the system is the surroundings. But we mostly look at the immediate environment to be the surroundings. In today's experiments, the surroundings are going to be water, and we'll use the idea that water has a very well-known specific heat capacity in order for us to determine how that change in heat for the surroundings of water relates to the change in heat for the system. So whatever happens to the system, the opposite is happening to the surroundings. If water is absorbing heat, that means our system is giving off heat. If water is releasing heat, then that means our system is absorbing heat. So we can use those in order to determine exactly what's going on. We're going to use this equation, Q equals mc delta T. In this case, this C is the specific heat capacity, and M is the mass. So the mass of the water times the specific heat capacity, which for water is 1 calorie per gram degree Celsius, times the change in heat will give us how much heat is either absorbed or released by the water. If the temperature of the water rises, this means that the water has absorbed the heat. If the temperature of the water falls, this means that the water has released the heat. So we'll have either a positive number for the absorption or a negative number for the releasing of heat. This will be opposite in sign for the surroundings. So whether our surroundings is the neutralization reaction, the salt that is dissolved, or the metal, the heat that is absorbed or released is opposite in sign than what you calculate for the water. You will also use the idea that water has a density of 1.00 grams per milliliter, and this will help us to go directly from the volume that we measure of the water to the mass of the water. In this experiment, we will be using a variety of chemicals. You will find your sodium hydroxide and hydrochloric acid in a jar or a flask in your basket. You will find 1 of 2 salts, magnesium sulfate or ammonium nitrate, in a small bottle in your basket, and you will find a metal. Most of the metals are in rod form, but there are a few that are in small cubes. The metal is labeled in green on the beaker. You're also going to use a coffee cup calorimeter, which is 2 styrofoam cups And while your lab manual says we're going to use a cardboard or cardstock lid, we're just going to use the regular lid that comes with these cups. There's a hole here for the straw. We can use that hole for our thermometer. Before you begin the experiment, you should go to Part C and set up your hot water bath. Be sure to record the mass of all of your metal pieces before you put them in the water so that you have the mass without any water on it. It will take some time for the hot water to reach a temperature that is hot, and it will also take some time for the metal to equilibrate. You may have small cubes of lead, which you would put in your test tube. What you're going to do is share a beaker with the person who is opposite you so that we can both use the same hot water bath. To begin, you're going to take 50 milliliters of each of your sodium hydroxide and hydrochloric acid. Pour one of these two chemicals into your styrofoam cup and then measure the temperature using the thermometer. You want to measure the temperature before the reaction starts, and these chemicals have been sitting at room temperature, so the two of them will be at the same temperature as each other. You'll need to rinse your graduated cylinder with deionized water, and then rinse it with a small portion of your second liquid. Then measure your 50 milliliters. This way you don't start the reaction with the residue of the chemical or have dilution from the deionized water. Add your second chemical to the cup and immediately put on the lid and place the thermometer into the lid. Try not to let the thermometer go all the way down to the bottom, and swirl the cup and then record the temperature as it changes every few seconds. What we're looking for is the highest temperature that it reaches. Continue to swirl while you are watching this. It should only take about a minute for the entire process to reach its peak and to start to cool again. You will have to repeat this part to have 2 trials. Once you've recorded the highest temperature, empty your calorimeter and rinse it with deionized water before you start part B. For the next part, you're going to be using weighing paper, which might just be scrap paper. But you're going to have to carry your salt back to your station. So what you want to do is fold up the corners to create a little container for your salt so it is less likely to spill. Then you can weigh this on the balance and then carry it back to your station without spilling. You're going to weigh out about 2 grams of your salt, but you need to take care of the weight of the weigh paper ahead of time. So place the weigh paper on the balance, make sure the doors are closed, and then hit the TAR or tare button. This will zero the balance, and then you can add your salt. Add most, but not all, of the 50 milliliters of water to your calorimeter. We're going to save some to rinse the salt. Take the temperature of the water and record this as your initial temperature. Remember to let it sit for 30 seconds so that you can get the temperature equilibrated. Go ahead and add the salt completely to the container. We want to make sure that we have the entire mass of the salt in there. So quickly use the remainder of your water to rinse off the paper into the cup. Add the lid and the thermometer, and using a swirling motion, mix the materials. You'll want to record the temperature every few seconds, and keep in mind that the lowest temperature is the temperature of the final temperature of our reading. For the third part, we're going to, like we did with others, start by putting in 50 milliliters of water and measuring the temperature. We can do this while we're waiting for the metals to continue to heat. We want the temperature to be steady, so make sure you leave it in there for more than just a few seconds. 30 seconds or so should be fine. And this will be your initial temperature. Remove the thermometer, but don't add the lid, because the next thing you're going to do is going to be adding the metal. Once you have reached a steady temperature, you will move your metals from your hot water bath into the cup. If you are measuring in the test tube, go ahead and put the thermometer directly into the test tube and make sure that the metal probe touches the metal itself. If you are measuring rods that are in the water, you can simply place the thermometer into the water and monitor the temperature. Don't let the thermometer rest on the bottom of the beaker because it might be altered by the hot plate. If you are using the small cubes in a test tube, put your test tube clamp around the test tube, loosen the clamp, and quickly transfer the metal pieces into the water. Add the lid and the thermometer and record the temperature as before.